Hi, my name is Carlo, and today I'm gonna present to you ways of using real-world data in your class. We're going to go through a very diverse set of examples of functions in Mathematica or in other Wolfram products such as Wolfram Alpha that can help you use real data in the class. So first of all, we're going to talk about sciences, and in particular, we're going to give some examples from chemistry. And then we're going to move on to the social sciences and talk about geography and statistics. Then we're going to give some less obvious examples, and we're going to show some interesting things about weather and about language and how we can make even teaching languages computable. So I would like to start with chemistry. So chemical data is a function in Mathematica, and it's one of a class of functions that usually end in data. So there are a bunch of isotope data, chemical data, and word data, weather data, and so on and so forth. So in general, these functions can be called without any argument to get a list of entities that are present. In this case, entities are going to be chemical compounds. There are almost 44,000 entities in chemical data, and each one of those entities will have a set of properties, and the possible properties are over 100. That doesn't necessarily mean that we have data for all of the 40,000 compounds and the 100 properties, but in many cases those slots will be filled. So let me show you. If you choose, say, 5 of those compounds at random, and you run the chemical data function on them, you get this simple structure representation. Now, as you can see, there are even some very complex examples of molecules. I really don't know what this one is, but it's pretty big. And there are many ways to access this data programmatically, and many things we can do. So one of the simplest example is to ask chemical data, okay, tell me what are all the hydrocarbons. So hydrocarbons are a class of chemical compounds, and just like one can ask for, say, what are the countries that are in the European Union, one can ask what are the chemical compounds that are hydrocarbons. And so if one asks chemical data, what are the hydrocarbons, one gets a very long list of chemicals that are expressed with their standard name. So it's a pretty long list. I didn't expect it to be so long. And then one can see various things about this compound, such as one can ask what's the size of those molecules. So, for example, what's the molecular weight is one of the possible properties of those chemicals. So another thing could be combustion heat. So as you probably know, many hydrocarbons are actually used as fuel. So one might want to ask, is there a relationship between the size of the molecule and the amount of heat that it will release when it's oxidized, when it's burnt? And there is in fact a relationship. And one can see that most of these chemicals fall on a line. So, starting from the smallest, methane, and then they seem to line up pretty well. But there are a couple of outliers, such as, so these guys below the line are the ones that are not very full of energy compared to their weight. On the other hand, the ones that are on top of the line are very energetic. They have a lot of combustion heat with respect to their molecular weight. So, for example, this guy seems to be an outlier, and we can ask chemical data, give me the molecule plot, which is this nice 3D representation. And most of the compounds that have a simple structure representation also have a molecule plot. So you can really bring this molecule to life. And if you used other software packages to draw these stick and balls figures, you know that it's not trivial to make one. And but here you can just basically extract it, and then this is just a 3D graphics object that then you can use for something else. Say you can embed it into another plot or something like that. But this is all very simple. This basically requires no programming at all. This is just asking chemical data, give me this information. So if one is a little more versed in programming with Mathematica, one can write something which is much cooler, such as a stoichiometry checker. So stoichiometry is the branch of chemistry that deals with the balancing of chemical equations. So you have things like, in this case, I have an example. You have some methane and some oxygen, and you say, let's see what happens if I combine methane and oxygen. What happens is, as everyone who has a kitchen knows, is they burn, and burning, they produce some carbon dioxide and some water, where you don't usually see the water because it's vapor. But so here I'm trying to say, okay, with 1 molecule of methane, 2 molecules of oxygen, I get 1 molecule of carbon dioxide and 1 of water. Is that correct? No, because our stoichiometry detector said it's false. So what's wrong? Well, it turns out that here I have 2 molecules of oxygen and water only has 1. So this can't be right. So maybe if I this here, well, in that case it works. So basically, sorry, you have 2 molecules of oxygen, that's 4 atoms. Carbon dioxide has another 2, dioxide, and then you have 2 more oxygen atoms from water. So that balances the oxygen, and then it turns out that the carbon, there's 1 here and 1 here, and then there's the hydrogen, there's 4 here and 2 times 2 in the water, so this is correct. But this can be done completely automatically. You just need to know what the name of the compound you're actually using is in Mathematica, and then you can do all sorts of stuff with this. Now, the next topic I want to cover is, as I said, geography. Now, there is another function in Mathematica called country data that contains a lot of information on all the countries in the world. So, obviously, as in the other example, if you call country data, open square bracket, close square bracket, you get a list of the countries that are present in country data. If you ask for the properties, you get all the possible properties that you can ask of those countries. Now, as before, just like the example I gave before, you can ask for certain classes of entities, in this case classes of countries. So just like before we asked for the chemicals that were hydrocarbons, this time we're asking for the countries that are in G8. Now the 8 countries that are in G8 are here, and one can ask for, say, the population. So this is a pretty simple example. You have Canada, France, Germany, Italy, Japan, Russia, United Kingdom, and the United States. Now, this is a pretty simple example, but there are a large number of properties in country data, over 200. And among those properties, you can ask for things such as, what does the electrical grid socket look like in that country in G8? And as it turns out, no 2 countries in G8 have exactly the same electrical plugs. Okay, some of them are somewhat compatible, but most of them aren't. And then one can actually use this country data to draw maps and do nice visualization. How is that possible? That's possible because inside country data there are polygons for all the countries in the world, and then one can even ask for a specific projection of those countries. So in this case, I wrote a very simple function that basically just creates a map of when given a list of countries and of number, whatever number you want to associate with that country. And then it uses this color data function that will take all the things that are closer to the minimum, and they will be colored in blue, and all the things that are closer to the maximum will be colored in red. Everything that's in between is going to be more or less white. So one can say, I want to look at all the countries in G8 and color them by government debt. And by doing so, one sees that, well, the US has very high government debt, and so has Japan. And the other countries are not so in debt. But probably there is someone among you that knows a little bit about choropleth maps and says, wait a second, what you're doing here is not correct, because you can't just pick a number and plot it on a map like that. You need to normalize it some way. And probably the best way to normalize government debt is to divide it by population. And here we can do that and see that basically the US is not much worse than Canada per capita or the countries in the European Union. On the other hand, Russia does pretty well, and Japan is really terrible. So here's a very simple and concise example where your students can actually explore large amounts of data, write one line of code and get maps exploring whatever property of those countries they're interested in. So this is an incredible and very valuable tool for if they're writing a paper or something, they can have this nice graphic object, those nice maps, and embed them in their presentation or in their paper. So here's an example that it's probably not so obvious to you. Mathematica contains a function that is called weather data that is connected to our servers and knows the data all over the world, and it's going back several decades, and it's updated to current conditions all over the world. So one can use this to, well, it would be kind of silly to use this to know whether it's sunny right now or not, but one can know about historical data. So one question I asked myself once was, does it rain more often in London or in Paris? Because London is famously very rainy, but I had the hunch that Paris wasn't so bad either. So I wrote this little function that basically calls weather data with the coordinates of the cities. This makes weather data look for the weather station that's closest to the coordinates of that city, and then you can ask for precipitation types that could be snow, rain, hail, and then a range of dates, in this case from the beginning of 2000 to now, and then counts the number of days where there is rain among the precipitations. So I ran this function on a bunch of cities, and I discovered that London is actually, at least in the past decade, has been less rainy than Paris. And they all fare pretty bad compared to other cities in the world. And almost half of the days in Paris, there is at least a little bit of rain. Now, this is interesting, but it's not a lot of data. And I want to show you here that one thing you can always do in Mathematica is by typing double equal and then writing something that you would write in Wolfram Alpha, you can get basically all the results in Wolfram Alpha and then extract them. So this is now getting some very rich content from Wolfram Alpha. And the advantage of doing this inside Mathematica rather than on the website is that you can actually, say, click on this little plus icon and get the actual data that is behind that pod. So to give you a nice example that it's already done, I clicked somewhere there to get basically, in this case, the annual precipitation in Paris, because I wanted to know Yes, okay, it rains almost daily, half of the days. But does it really rain a lot, or is it just small showers? So in this case, what you can get is precipitations amount. I think it's not daily; it's not yearly; it's more monthly, and you can get the data and then you can plot it. So this is an example of data that is not in Mathematica, but it's in alpha, and there is a nice programmatic way of accessing it in Mathematica. Now, another example that's a little more exotic is the fact that you can use programming and actual hard data to look at languages and at the ways in which they differ. Here is a list of all the languages for which Mathematica has a dictionary, and they range from very common ones like English or Arabic to Breton and Irish Gaelic and Scottish Gaelic, which have many less speakers, not to mention Latin, which has basically no native speaker right now. So one can look at what quantity of data is present in those dictionaries. And one will find out that some languages have far, far more words in the dictionary with respect to English. And I suspect the main reason is that English is a language that doesn't really change much. Like, verbs only have very few forms. Well, other languages such as, one that I know of is Italian. For every person, I am, you are, and every verb, every mode, and every time of verbs have a different form. So all those things will pop up in the dictionary and they will count. So here's a logarithmic plot of the number of words in dictionaries. So from Finnish to Esperanto. And English has about 100,000 words, so it's more or less middle of the pack. So a dictionary lookup can be used to search dictionaries in various ways, and one can come up with functions that are somewhat more creative. So, for example, if I have a word and I want to know what's an anagram of that word. For example, lemon. Well, one only has to basically get the characters in that word and sort them and see if two words have the same set of characters when they're sorted. Then it means that they are one the anagram of the other. So if one looks for the anagrams of lemon, finds that turns out it's another fruit, that's its anagram. Another example would be palindromes. So palindromes are words that you can read from one side, from left to right, or from right to left, and they stay the same. And it turns out that palindromes of over 5 letters, because this is how I defined it, these are palindromes of 5 letters or more in English, are this pretty short list. Now, another thing I was thinking, but it doesn't really work that well in English, works better in Italian, is sometimes you need a rhyming dictionary. Now, the spelling in English doesn't give you any sort of clue of whether two words rhyme, but that's not the case in Italian. In Italian, if two words end with the same ending, they will more or less always rhyme. So, in this case, I was looking for all the words in Italian that end with ello. So all those words rhyme. So suppose I'm writing some sort of poem or a song and I can't find a rhyme with something. I can actually ask Mathematica for all the words that rhyme with something else. Now, if one wants more detailed information about one particular word or some feature of language, there's another function in Mathematica called word data. Now, word data only works with English, unfortunately, but has a lot of interesting properties. So, for example, to think about the example we were talking about earlier, turns out word data has a phonetic form. So, you can use word data to actually write a rhyming dictionary. Another example are synonyms and antonyms that can be used to build a network of words that mean the same thing, or American spelling and British spelling, and so on and so forth. So a very simple example one can use is to use word data to recognize parts of speech. Now, since word data only knows about one word at a time, it doesn't know whether boy means the noun boy or the interjection, oh boy. You have this cases where it's not really sure. But in most cases it is sure that and is a conjunction and the is a determiner. Another thing one can do, since we have all the different spellings of words in British and in English, in British English and in American English, one can ask for data for a list of all the words that have actually different spelling in English and in American English and in British English. Turns out that those words are about 3,000 and are things such as abridgment, acer, and achromatize. So those are only the ones that are at the beginning of the alphabet. The thing one can do is, once we have all the words that have different spelling, one can get a rule list with, in this case, the American spelling, and then a nice rule goes to British spelling. So to see how this works, we can take this string. When I park my car at the freshly painted curb next to the parking meter, I get paint on my tire and change its color. And once we turn all the American words to British versions, we can see that spelling of curb is different, spelling of color is different, tire, and meter, and so on and so forth. So this is a fun little example of ways in which one can use data and programming to teach languages, not only science. Now, in conclusion, I want to tell you that this slideshow only covered a very small part of the data that's included in Mathematica. If you look in the documentation, there is a guide that is called Scientific and Technical Data, and there are learning resources and examples, and as well as a lot of other functions that I haven't covered here that talk about, say, subatomic particles, or elements, or cities, or the genome as well. And if you look inside any of those, you'll see many examples of things that can be used in the classroom to teach biology, for example. Now, the reason why this is important is that Mathematica is a unique environment to mix together programming, even very basic programming skills, and data. There is nothing else that I know of where you can write something like the stoichiometric balance function that we wrote before, or a rhyming dictionary, because only in Mathematica you can bring together data, so knowledge about a word, and a very rich programming environment, which is very simple as well. Now, data and computation don't need to be used only in STEM education, but can be used also for teaching languages and literature. Now, what we showed today barely grazes the surface of what can be done. If you want to see a more compelling example, you can look at, for example, you can search for any Shakespeare's play on Wolfram Alpha, and you will see that there are a bunch of very interesting computable facts about all of those plays, such as the most frequent words, or the most frequent clusters of two words, such as my lord, and then the reading length of all the appearances of characters, the reading length of all the acts, and also the appearances of various characters. So, and this is, again, another example of things where maybe you don't find what you're looking for in Mathematica, Well, there is a function in Mathematica called Wolfram Alpha that allows you to access everything we have in Wolfram Alpha. So either use that or get Wolfram Alpha Pro and download it directly from the site. Thank you very much for your attention.